Consider the following example first. We have a Chinese general that wants to count his soldiers. Suppose that we know that there are X soldiers and this X is less than 1,000 soldiers. So the general asks the soldiers to stand in rows of 7. So when the soldiers stand in row 7, the number of soldiers left over was counted by the general and it was 5. So he only counted like the leftover. Then he asked them to stand in rows of 11 and then rows of 13. When they stand in rows of 11, the leftover was 3. When they stand in rows of 13, the leftover were 2. So we need to find the number of soldiers. Of course, now without counting because we don't have them, but we have these informations. So we are looking for the number X. But X satisfies the following. When we divided X into rows of 7, that means when you divided X by 7, the remainder was how much? 5. So X is congruent to 5 mod 7. That's how I can translate this. When they stand in rows of 11, so that means when you divided them into 11s, the leftover was 3. So X is also congruent to 3 mod 11. And at the same time, X was congruent. So when I divided, when they were divided into rows of 13, so when we work on modulo 13 now, it was 2. So this is a system of congruences. It's kind of similar to a system of equations. So you need to find X that will make all these equations true. Sorry, all these congruences true at the same time. We state the Chinese remainder theorem. Suppose that you have a system of equations. Now, one thing we require here is that for this to work, I mean, if they're not pairwise, if these numbers, we require that m1 through mn, so these numbers, we want them to be pairwise relatively prime. Means what? Means that the GCD of m1 and, okay, first, sorry, this is written twice by mistake. Okay, so from here to here. So that means GCD of M1 and M2, M1, M3, M2, M5. So in general, MI, MJ is equal to 1. For any I and J, for I and J between 1 and N. And of course, I not equal to J. So if this is satisfied, if I have a system of equations in this form, so I do have requirements that all these modulos should be relatively prime. Then there is a unique solution modulo M. Of course, now there will be infinitely many solutions, but there's only one modulo M, where this capital M is M1, M2, Mn, the product of these moduli. And this solution is given by this expression. Well, notice A1 is given, so A1 is not hard to find. M1 is not hard to find because M1 is going to be just M over M1. So this is the meaning of capital MK. M sub K is capital M over MK. So MK, if you want, is the product of all the M's except small mk. Okay, like it's M1. For example, M1 is, capital M1 is M2 times M3 up to Mn. Capital M2 is M1 times M3. You skip M2 times to Mn, and so on. So for example, the last one, Mn, is going to be M1 up to M. The one that comes before Mn is M sub n minus 1. So this is not hard to find. But yk is going to take some time because yk is what? It's the inverse of mk modulo, capital Mk's modulo small mk. Okay, so you need to have this in front of you to be able to solve that system of congruences. Okay. So let's try a simple example first. There are certain things whose number is unknown. When divided by 3, the remainder is 2. So that means, for example, if I let x be the number, okay, so when x is divided by 3, the remainder is 2. So that means x is congruent to 2 mod 3. When divided by 5, the remainder is 3. So x is congruent to 3 mod 5. And when divided by 7, the remainder is 2. That means x is congruent to 2 mod 7. So I want to find this x. And I will use the theorem that we just stated, the Chinese remainder theorem. Remember that the solution is given by x equal a1 capital M1 I1. So let me write it here. X equal a1 M1 Y1, okay, or congruent, plus a2 M2 Y2 plus a3 M3 Y3. This is all what? Modulo capital M. Now, capital M, okay, first, this is your A1, and this is your small m1. This is m2. This is m3, small m3. This is A2, and this is A3. Okay, so M is M1 times M2 times M3. So this is M1, M2, M3, which is 3 times 5 times 7, which is 105. Okay, now capital M1 is equal to M over small m1, which is M2 times M3. Okay? So this is 35. M2 is M over M2, which is M1 times M3, and this is 21. And capital M3 is M over M3, which is M1 times M2, and this is equal to 15. Okay, then I have to find, so here, do you see I have A1, so I'm looking at this right here. I have everything except small y1, small y2, small y3. But what was yk? If you go back, yk is the inverse of big mk modulo small mk. Okay, that means what? That means that y1 times m1 must be congruent to 1 modulo small m1, because y1 is the inverse. Okay? So again, recall that this is yk is an inverse of mk modulo mk. This means that yk, if you multiply it by big mk, this should be congruent to 1 modulo small mk. Now here, I'm choosing a simple example, so I can find these by trial and error. So this means what? This means big M1, so this is like 35 multiplied by Y1 is congruent to 1 modulo small m1 is 3. Now here's the good stuff. 35 can be reduced modulo 3. If I reduce 35 modulo 3, this is gonna be 2, because 33 is divisible by 3. Now y1 doesn't have too many options. Y1 can be either, it cannot be 0, the inverse can never be 0, it's going to be either 1 or 2. Clearly it's not 1, but it's 2, because so here y1 is congruent to 2. You always find the smallest positive integer. So y1 is congruent to 2 mod 3, so you pick y1 to be 2. Why y1 equal 2 works because 2 times 2 is 4 and 4 is 1 mod 3. So here I found this. In a similar way now, I do small y2 times capital M2 is congruent to 1 modulo small m2. I want to find this y2. So I know here this is 21 times y2 is congruent to 1 mod m2 is 5. Now here actually we're kind of lucky because 21, I want to find y2. But when I reduce 21 mod 5, this is already y2 because that's going to be 1. y2 is congruent to 1 mod 5. So y2 is equal to 1. Always you choose the smallest positive number. And finally, I need to find y3 times m3 congruent to 1 mod small m3. Okay. So this means that y3 is times big M3, so 15 multiplied by y3 is congruent to 1 modulo 7. Again, here we were lucky with the numbers. What happens is that when I reduce modulo 7, this 15 becomes 1. So this means that y3, so this is 1, modulo 7. So this is y3 is congruent to 1 mod 7. So then y3 is equal to what? To 1. Now I put everything in the formula above. So then, as a result, the solution is this. X is congruent A1, which is 2, times capital M1, which is 35, times times Y1, which is 2, plus A2, big M2, Y2. A2 is 3, big M2 is 21, Y2 is 1. And then, similarly, I'm going to have 2 times 15 times 1. This is mode what? Mode capital M. What's capital M? 105. So then, X is constant. If you find this number, you're going to get 23 mod 105. Of course, after reducing mod 105. This is going to be our solution. So it's not an easy process, especially that it's not a short process. I think it's not too hard because it's just one step that you keep repeating, and all these steps that you have learned how to find them before. But the only thing that could make this a bit more difficult is when the numbers are not that small. So it's very hard to guess or find the inverse by trial and error. In that case, you need maybe to use the extended algorithm for some of the cases. But that's, of course, it's doable. It's the same idea that you repeat. Now, there's another approach, okay, to solve this. This is again another method that you can use. You can consider it as an alternative method to the previous one. So I'm considering the same system because I know its answer, and I want to show you how I can find its solution using a method called back substitution. Okay. Now we start by so here's the idea. I'm gonna start from the first equation, and I'm gonna write this. The meaning of x congruent to 2 mod 3. This can be written as x equal 2 plus 3 multiplied, let's say, by some integer k1. That's the meaning of this. And then I'm gonna put this value instead of x right here. Okay, so instead of having 3 equations, I'm going to have 2 equations. So I do substitutions here till I have only 1 equation at the end. And of course, the fact that these numbers are relatively prime, then I will be able to solve at each time. So when I replace this here, what happens is that this equation becomes 2 plus 3k1 is congruent to 3 mod 5. Move this 2 to the other side, so you get 3k1 is congruent to, let's say, just 1 mod 5. Okay, now because the number 3, which is the one here, the one that you see here, small m1, and 5 are relatively prime, then the inverse of 3 exists. I multiply by the inverse, I get k1, and then I repeat the process again. So let me show you how I do this. So start from the first equation. I'm gonna write, so from here, we're gonna write then there exists k2 or k1 in z such that x equal 2 plus 3k1. Now substitute this x, so substitute x by 2 plus 3k1 in the second congruence. Okay, so this means that you get 2 plus 3 multiplied by k1 is congruent to 3 mod 5. Okay, now let's try to solve here. So I want to find k1 here. So this means that 3 multiplied by k1 is congruent to 1 mod 5. How did I get this? Well, I subtracted 2 from each side. Okay. Now, by trial and error, because what k1 can be, I mean, you can just find 3 times k1 is congruent to 1 mod 5. You can find the inverse of 3, or you can find k1. I mean, here you're just going to use trial and error because the possibilities are not much. Okay, so 3 times k1 congruent to 1 mod 5. By trial and error, k1 has to be 2 because 3 times 2 is equal to 6, and 6 is congruent to 1 mod 5. Okay, so multiply k1 is congruent to 6, congruent is k1 is congruent to 2 mod 3. So k1 is congruent to 2 mod 5. Okay. This means what? This means that k1 is equal to 2 plus 5 times k2, and k2 is another integer. So here's what I do. I know that x is equal to 2 plus 3k1 from here on the top. So now k1 is 2 plus 5k2. So substitute k1 by 2 plus k2 in x. So this means that x is equal to 2 plus 3 multiplied by 2 plus 5k2, which means x is equal 2 plus 6 is 8 plus 15k2. So I started with x equal this, now x equal this. Then I'm going to substitute this one in the third equation. So substitute x equal 8 plus 15k 2 in the third equation, or the third congruence. Okay, so I get x, what was the third congruence? X congruent to 2 mod 7. So then I have this, so it was x congruent to 2 mod 7 implies 8 plus 15 k2. This implies what? Let's reduce mod 7. So when I reduce 8 mod 7, this becomes 1. 15 mod 7 is 1 times k2 congruent to 2 mod 7. So then k2 is congruent to 1 mod 7. So then k2 is equal to 1 plus 7 times some number k3. Again, k3 is an integer. Okay, now remember that this was x here, the one that we just used recently. So instead of x, instead of k2, I'm gonna put this. So now replace k2 by 1 plus 7 k3 in x. So x becomes 8 plus 15 times 7, or 1 plus 7 k3. Okay, this is not erasing. That's weird. So 15 is equal to 1 plus 7k3. So then x is equal 8 plus 15 is 23, and then you have 15 times this is 105k3. Well, this is exactly what we got previously. What we got in the previous method was x congruent to 23 mod 105, which is the same as this. So these two are equivalent. Okay, so this is how you solve this system using the back substitution method. Again, use the method that you prefer. It's not required to use this or